So when we want to bungee jump from 2 miles up, and we have 3,200 meters, that's the height that we're falling. What we need to do is we need to tack on a whole bunch of bungees together. Okay, and one of the properties that happens is if you take two bungees together. So let's just take these two. Each one has the same length and the same K. The combination obviously has twice the length, but it has half the K. So as we string them together, the K, the stretchiness goes way down. And if we happen to have bungees that we put together and they're the same, but we kind of bind a bunch of them together, if we take two of them that each have the same K and L, the combination of the two has length L and twice the K. All right, so this is how we can modify both the length and the stretchy constant and for any of these things. And now I could, if I wanted to make a bungee that's twice as long but the same K, all I would do is just make it twice as long and then strap two of them together, and that would do it. In this case, I'm going to use the K from the previous example, which was 69 joule per meter squared, and we're going to be jumping from 3,200 meters. So essentially, what I'm going to do is I'm going to tie them end on end like this and see where this gets me. And I'm going to tie n of them together. So the total length will be n times L. Okay? And then it'll stretch out a certain amount, this bungee, and this total has to be equal to 3,200 meters. So that way I reach the ground. So this is going to be equation one. This has to be true for jumping. The other one is to figure out the energy, and we did that in the last time. We found that for me at 70 kilograms, jumping from 3,200 meters, that was an equivalent gravitational energy of 2.2 times 10 to the 6 joules, and this is going to be equal to 1 half times the K, 69 joule per meter squared. But notice, since I have n of them in a row, the K is reduced by a factor of n. Because if I had two of them in a row, it's reduced by 2, and so on. And then we have the stretch, x squared. Okay? These are the two things that have to be the case. One, I have to have the right length to reach the ground. And two, I have to absorb all of the energy with the right amount of stretch. And in this case, my length, if I just use the same length as I did before, would be 30 meters. So what I have now is two equations and two unknowns, and it's just math. So after this point, there's not really any physics involved. It is just solving the equations, two equations and two unknowns. The easiest way is to take equation 2, multiply by n on both sides, and divide by 2.2 times 10 to the 6 joules. And so what I'd get is n is equal to 1 half. I get the 69 joule per meter squared times x squared all over 2.2 times 10 to the 6 joules. And then I plug this into equation into equation 1. I'll simplify the numbers a little bit. This is 1.6 times 10 to the negative 5. 1 over meter squared. That's what the units would have to be, times x squared. So now I plug this into equation 1, and I have 30 meters times 1.6 times 10 to the negative 5, 1 over meter squared, times x squared, plus x equals 3,200 meters. Okay, and I can change this, actually, just bring the 3,200 meters over. I can do a minus, and then it equals to 0. At this point, all we have, so this part of it here is 4.7 times 10 to the negative 4, 1 over meters, just that number. Okay. So at this point we have a single equation with x. It looks a little messy, but let's rewrite it so that way we end up with something that is at least a little bit cleaner. So we're left with the equation 4.7 times 10 to the negative 4, 1 over meters is there, times x squared, plus x minus 3,200 meters equals 0. And so this is A, this is B, this is C, and we know from just the quadratic, this is the quadratic equation, so we get, negative B plus or minus the square root of B squared minus 4AC, 4 times 4.7 times 10 to the negative 4, AC times negative 3,200 meters. This is 1 over meters. So the units are all going to cancel inside the square root, which is good. All over 2a, which is 2 times 4.7 times 10 to the negative 4, 1 over meters. Okay, so that's just the quadratic equation. And in fact, it simplifies down a little bit to about negative 1 plus or minus the square root of 7 over 2 times 4.7 times 10 to the negative 4, 1 over meters. Okay. There are two solutions. So one of them makes sense, one of them doesn't. The one that makes sense is about positive 1,750 meters. The one that doesn't make sense is negative 3,880 meters. This one's not going to make sense from physical points. Going back into equation 1, we're able to find that the n for this one is 48. So if we happen to take bungees of 30 meters with a K of 69 joule per meter squared, and we string 48 of them together, they will stretch by 1,700 meters, and we'll be able to reach the ground at about 3,200 meters and absorb the entire energy for a 60 kilogram person. Okay, clearly this is, I do not endorse jumping out at 2 miles unless you are an absolute professional. There are so many things here that could go wrong. The assumption of K, the limitations of an actual bungee, we haven't even talked about that. But this at least gives you a sense. And although this page is pretty messy in terms of mathematics, the initial setup really was just, is the length long enough and does the energy match? And those are the two things.